Hello, everyone. Ready to go. We're going to walk through this a little bit of a worksheet. Hopefully it just gives you a little bit of practice on integrating, which I know you're pretty good at already, and then we'll look at tangent lines and a little implicit differentiation on the bottom. So number one, I don't suspect you'll have a lot of trouble integrating that. As you know, you can bring 15 out front. It is a multiplier, so just bring it out front. And now focus in on your x to the fourth. Power rule says we can up that by a power and then divide by the new power. Simplify it, and we're looking at 3x to the fifth plus c. One of those basic integrations. And then hopefully they get progressively harder. Here, when I'm looking at this second integral, I see two things multiplied, and I know that I don't have a great technique for working with the product of two things and integrating that. So either I use a u sub as one of the techniques that we've learned so far, or perhaps I can get around it by making it into a polynomial. And indeed I can by simply distributing that through. We can turn this into polynomial style and deal with each term individually. So go ahead and distribute. Giving us 15x to the fourth plus 20x cubed dx. Next, deal with each one separately. I'm sorry, I missed the negative. So we've got a negative 15. Like problem number one, we brought that 15 out front, so I'm just going to kind of imagine in my mind, I'm going to go ahead and bring the negative 15 out, and now I'm going to integrate x to the fourth. So that's going to be an integral where it goes x to the fifth divided by 5. The next one, the 20, is out front. Integrate x to the third. That's going to be at x to the fourth power up, divide by the new power, add a c. Simplify where we can, and we're looking at negative 3 x to the fifth plus 5 x to the fourth plus c. Problem number 3, quite similar, actually probably easier than the one we just did. Go ahead and you could bring your 4 out front and do it at the end and make it an integral that looks like that, or if you'd rather, you could distribute it through and work with an integral that says 12x squared minus 4 dx. Either way, you'll get the same answer and should be fine. Stop the video if you want to do it right now and then come back on 4. Number 4, when I look at this, I see two things multiplied. The first group that's cubed, and the second group where I have 16x to the third. I would not really care to expand that. It wouldn't be horrible, but maybe I don't need to. There's that thing called u sub, and if I could let that, my more difficult term of this, expand into just u, or simplify to u, it would make integrating easier. And with a quick inspection, I see that the derivative of 4x to the fourth really will become something x to the third. Matter of fact, it'll be 16, won't it? This should play out very nicely. So let's just set up a little u sub over to the side and say, let's let u equal 4x to the fourth plus 5. The derivative of that is 16x to the third dx. I have exactly that. This is equivalent to du. So I can take this and rewrite my integration in terms of u. U to the third du equals, the integral would be u to the fourth divided by 4 plus c. Now let's switch it back into x's by back subbing what u was equal to. 4x to the fourth plus 5 raised to the fourth over 4 plus a c. And we're done with that problem. Number 5, kind of similar to the last one. I see something raised to the fourth and I'm not really into expanding that. What if we tried a little bit of u sub? If we let the inside of this more difficult looking term or factor be u, would the derivative of this be something that we could work with? And I think so. So u sub, let u be x squared plus 2 then the derivative is 2x dx. Checking back up here, I really need 6 of those, so let's introduce a multiplier of 3. Multiply both sides by 3 to be fair. And we have 3 du is equivalent to a 6x dx. Back to our integral. We have the integral of u raised to the 4th. And 6x dx is a 3 du. So we're going to replace that with that 3 du. The 3 can come forward, and we can integrate u to the 4th du. That gives me 3 u to the 5th over 5. Add a power, divide by the new power. In terms of u, this is great, but let's get it back to x's. So back sub for our u, and we have x squared plus 2 over 5 plus c. Number 6, maybe you're thinking u sub, and that's always, I mean, it's good to check things out. If I did the derivative of cotan, let's say I was thinking, let's let that be u, then du would be equal to, what's that, negative cosecant squared x. That's not what I have there. I don't have the squaring, so that doesn't really pan out. What about we did the other one? Let's let this be our u. U equals cosecant x. Well, the derivative of that would be negative cosecant x cotan x. And if I let this be u, this is all I've got to play with. That's more than, this will be a dx there, more than what I'm coming out with. But, this spurs a memory to me. The derivative of cosecant is negative cosecant cotan, and that's exactly what we have. This really is a very straight up integral. The integral of cosecant cotan x is negative cosecant x plus c. Why? Because if I took the derivative of cosecant, I've got a negative on this one, the derivative of negative cosecant would be that negative, and then a negative from the formula cosecant x cotan x, and then dx. Minus minus makes plus. Perfect. The derivative of cosecant gets us this, which is what we were working on, so the antiderivative of cosecant is that. Number 9, you know what, I skipped a couple, but I hope you're fine with that. Try doing those other two on your own. Express each definite integral in terms of u, but we do not have to evaluate it. Actually, let's evaluate it. That will be good practice. So, I'm noticing an x squared here and an x. That means that this is 1 degree lower than this one. My u could be this bottom factor. So u, let it be 3x squared plus 2. Then du is equal to 6x dx. I have 12, so let's double things. Multiply by 2, and we are at 12 of them. So I have 2 du equals 12x dx. That is a nice du sub there. Oh, a 2 du, isn't it? Okay, so we're ready to integrate. This will equal, notice that negative, I'm going to pull it out front. The integral from, I cannot use 0 and 1 now that I'm switching things into u, so be very careful about that. This will be u to the 2nd, because we said let all of this represent u. I'd have 1 on top, 1 over u squared. 12x dx is a 2 du, so I'll bring my 2 out front. And now let's update our intervals. The intervals will look like intervals in terms of u. Well, we have the statement right here that tells us how to do it. U is equal to 3x squared plus 2. When x is 0, I plug in 0 and calculate. U becomes, oh, lie. U becomes 2, doesn't it? So there's my bottom number. When u is 1, the upper interval limit, plug in 1, and this is the one that comes out at 5, doesn't it? So 3 plus 2 is 5. Now my upper interval is 5. I just was able to switch this up and work into u's. Now we just need to integrate. This will be negative 2 integration from 2 to 5, u to the negative 2 du. I like getting them written just exponentially, not as a fraction format, like it was back here. So negative 2. The integral of u to the negative 2 is u to the add 1, reduces our power to negative 1. Well, actually it increases it to negative 1, and then divide by the new power, which is negative 1. This will be evaluated from 2 to 5. I can simplify within this bracket a little bit. That'll be a positive 2. Why write positive? So that's a 2. And this really means 1 over u. And I want to evaluate that from 2 to 5. So, fundamental theorem of calculus tells us how to handle these. I'm going to have 2 times whatever this shakes out to be. 5 goes in. Remember, you start at the top, so I get 1/5 minus bottom 1, 1 over 2, and then I'll let you do the fraction work from there, but we've got it pretty much done. Find the equation of the normal line to the function at the given point. The word that's probably kind of putting a little kink in your step right now is the word normal. Normal lines are perpendicular to the tangent. So that tells me if I can get my tangent slope, then opposite reciprocal will get me the normal slope. Well, this looks like a fun one to do the derivative of. So to get the tangent, the slope at the point of tangency, I am going to take a derivative. So y prime is equal to, the power comes down, 2x minus 2. Power gets reduced by 1. So if I subtract 3/3, I'm going to go to negative 2/3. Multiply by the chain rule. Derivative of the inside is a 2. That creates 2/3. And then I'd have this over, because my negative power is going to drop this down below, and I'd have the cube root of 2x minus 2. The 2 on top means to square this item. And that's our derivative. I want to know the derivative at the point of tangency, so at negative 3. So y prime of negative 3 will look like 2, 3, cube root, 2 times negative 3 will make this negative 6 minus 2, and then square. It gives me 2. 3 cube root of negative 8. Ooh, nice. Squared. It gives me 2 over 3 times negative 2 quantity squared, because the cube root of negative 8 is negative 2. And it gives me 2 over positive 4 and 3 makes 12. And that gives us 1/6. Hey, not bad. Kind of liking that. So the tangent line slope is 1/6. Therefore, the normal line slope is the opposite reciprocal. Normal line slope, negative 6. Writing the equation of the normal line is y minus y sub 1, which will be plus 2, equals the slope times x minus x sub 1, which gives us a plus 3. Not too bad. Last one, implicit differentiation is used or useful when I have an equation that has an intermixing of x and y variables, making it quite difficult here to solve for just y. So probably better, let's just try to use the technique of implicit differentiation. So I'd have 6x dx dx, but I don't really need to write down dx dx. I'm going to think of this 2x multiplying by the y. So the derivative of 2x is 2 multiplied by y, added with derivative of y is 1, and then dy dx. So I'd have, and then multiplied by the first term, so with a 1 dy dx. Minus derivative of y squared would be 2y dy dx equals 0, because the derivative of a constant is 0. What I want is what dy dx is equal to. So I'm thinking send these two terms to the right, send them over to the other side, keeping these two terms because they have dy dx right here. So I'm going to have 2x dy dx minus 2y dy dx equals, pushing them over is going to give me a negative 6x minus 2y. And notice that they have a like factor here, so let's factor the dy dx forward. That leaves us a 2x minus a 2y equals a negative 6x minus 2y. We can easily get dy dx by itself through division. I'm noticing everything's even, so let's divide each and every item by 2. That'll give me negative 3x minus y over x minus y. And this is dy dx. A little implicit, not hard to do. You usually end up trying to gather the similar terms on one side and factor it out and solve it. Hope this gives you a quick refresher, you guys. See you later.